Hello, everyone. My name is Zeng, and today I'm going to talk about a system that we built called Libra, which used a divide and conquer algorithm to verify the forwarding tables in huge data center networks. And this is a journal with my colleagues Shidong, Fei, Vimo, Mickey, Junda, Nick, and Amin in Google and Stanford. I want to start my presentation with a very famous quote from Charles Dickens in his novel, David Copperfield. It says that, "My dear friend Copperfield, accidents will occur in the best regulated families." So in our network world, what is the best regulated families? Data centers. Why? Because in the data centers, there are homogeneous machines and switches, and there's only pure IP forwarding. Very few security concerns. Everything is considered trusted. There's no city human users. And network admins have full control of all the devices. However, as Dickens says, even in data centers, accidents can still happen. So this is a figure shows the tickets that I collected about the data plan problems in the Google's production data center. The x-axis is time, and y-axis is the bug account. And here I show three very common data plan problems. A forwarding rule is missing, or there's a forwarding loop, or there's a black hole. And as we can see that every few days, a ticket the problem can occur. And remember that each of these tickets, even diagnosing that there's a missing rule or there's a forwarding loop, can take a very long time. So each of these tickets can be very expensive to troubleshoot. So why getting the networks right is so difficult? First of all, modern networks are difficult. Modern networks are very complex. There's complex interaction between multiple protocols on the same switch, and there's complex interaction between state on different switches. As a result, there are multiple uncoordinated writers that write simultaneously to the forwarding state. For example, BGP and OSPF are two popular routing protocols, and they can write to your forwarding tables simultaneously. So operators normally cannot observe all the state because the state are distributed, and neither can they control all the state. So how do we do with this problem? One solution is use what we call static data plan verification. So what is static data plan verification? The goal of the data plan verification is to verify data plan's logical correctness. The example failures that we want to capture are forwarding loops, black holes, or network partitions. And the input to these static checkers are, number one, destinations. These destinations can be the host addresses or the switch's loopback addresses. And number two, rules. These are just forwarding rules, which are the match plus action tuple. And finally, the topology, which are how the network is connected together. Note that here we are talking about the data plan's logical correctness. In other words, we want to capture the data plan's problem. For example, there's a forwarding loop, but it won't tell you that why the forwarding loop is there in the first place. So it won't tell you that what kind of. So this is independent of the control plan verification. So here we have an example network that has 4 routers and 8 rules, 2 in each router. If everything is correct, then packet destined to IP2 will go from A to C to B. Now, for some reason, if in the router C, instead of the forwarding packets to B, router C decides to forward the packet back to A. So this creates a loop, and this is the exact problem that we want to capture through this static data plan verification. There are 2 main challenges of the static data plan verification in data centers, and they are the main topics of today. And the first one is the basic constant rule changes. In the large data centers, link can go up and down, and there are constantly route recalculation. And network admins may try to install new policy, etc. And what's worse, as I will show later, careless snapshot of your forwarding tables may result in false positives. And the second problem is purely due to the large scale of data centers. There can be tens of thousands of switches, millions to hundreds of millions of rules in the data centers. How to finish this verification in a reasonable time frame? So let's start from the first one. Before I talk about how to tackle the constant rule changes, let me introduce a very important concept called forwarding graph, which will be used throughout this talk. A forwarding graph describes how the network treats the class of packet destined to a specific destination. for example, in this network, all the packets that are destined to IP2 goes from A to both C and D, and both C and D will forward these packets to B. And since IP2 is a local address for B, B will just deliver the packets. So this behavior can be abstracted using the forwarding graph on the right, where each node is a physical node, and each edge marks the forwarding direction of the packet. Now let's look at this snapshot problem. Assume that in our network, two things happen. And there's an event E1 where A deletes rule A to D. We delete an edge from our forwarding graph. And there's an event E2 where D deletes rule D to B. And if we put these two events on our timeline, we can basically have three states: initial state plus E1, and initial state plus E1 plus E2. Now our static checker, which is represented as this camera, wants to capture this problem, capture the state of the forwarding plane. So it does that by downloading the forwarding tables from the switch themselves. So let's assume that this checker downloads the table from A first, hence it lends the event E1. And then it downloads the table from the router D, and then it lends the event E2. So locally, this checker can reconstruct the timeline by putting the E1 and E2 on locally, and it will learn the initial state plus E1, and initial state plus E1 plus E2. All these three states are okay. There's no black holes, no forwarding loops, nothing. So this is good. However, alternatively, the checker may choose to download the forwarding table from D first, and then we download the forwarding table from A. Now, remember that this downloading sequence is completely arbitrary. You can download it in any order. So in this particular case, we will learn the event E2 first, and then we learn the event E1. So locally, when the checker is trying to reconstruct the timeline of the forwarding plane, it will learn the initial state and the final state. They are both okay. But the initial state plus, there's a middle state, which is initial state plus E2, has a black hole in it. Because A forwards the package to D, and there's no rule going forward the package from D to other places. So there's a black hole. However, this is a false positive because this state never happens in the real world. So why will we have this false positive? The core problem here in our in this snapshot problem is that we cannot take a global snapshot simultaneously across the entire network. Otherwise, we will know either the initial state plus E1, or the final state, but never the false positive state. However, this is a physical limitation. We just cannot do that. We just cannot take a global snapshot simultaneously. So how do we do about it? Our solution is to focus on the events. That is the rule updates, not the state. That is the forwarding tables. So an event is just a rule update with a timestamp on it. Let's assume that our checker listens to all these rule updates, and then by looking at the timestamp, you will know that the E1 happens before E2. Hence, you will correctly reconstruct the forwarding state. You won't have that false positives. However, this approach is based on the fact that we have an accurate timestamp. However, in the real world, we don't have the true global clock for these timestamps. And this is a well-known problem in distributed systems. So the solution is to leverage the imperfect global clock, which is usually provided by NTP or network time protocol. NTP has certain precisions of epsilon equals to 1 to 100 milliseconds, and every event can be considered to be bounded by 2 epsilon. And we should only consider a snapshot when we think it is stable. So what do I mean by stable? Let's consider these two cases. Now, locally, we have logged the event E1 and E2, and I put a gray shaded area around its timestamp, which are 2 epsilon wide. So in the first case, we basically have 3 stable states. We have the initial state plus E1, and the final state. And for each of these three states, we know that this state actually happened in the network. However, if E1 and E2 is very close to each other, their shady area may overlap. Now in this case, in the shady area, it's possible that E1 happens before E2. It is also possible that E2 happens before E1. We don't really know. So in this case, we should only report two stable states, which is the initial state and the final state. One may ask that will never ever be stable, right? Because after all, we just discard a lot of shady area. We will discard too much of them. So in order to answer that, we look at a production Google data center. And we find out these Lua updates are very bursty. So during the 24 hours period, we record over 28,000 events. If we look at the events themselves, we will find that 95% of the events happened within 400 milliseconds of each other. In other words, they are in most of the time, the network is silent. And if we look at the time, assume that we have epsilon equals to 100 milliseconds. 99.9% of time, the network is stable or the network is silent. So most of the time, our checker should be able to find out the stable state. But if one is truly paranoid, how about this transient state? One way we can deal with this transient state is that we can report the potential problems by doing all the permutations of these events and report problems. But we need to tell the users that these problems they are potential problems. They are not guaranteed to happen in your network. In other way, network operators may not care about this transient state anyway because they are so short-lived. Think about it. During the 24 hours, there are only 0.1% of time the network is unstable. So it's so short-lived that it probably won't cause any real problem in the application level. So let's go to the next challenge, which is the large scale of the data center. Once we got this stable snapshot, we can do the static verification. A naive static checker is quite easy to implement. Basically, you can load all the rules in your memory, you pick one destination, you pick one ingress port, and you simulate the packet behavior. And you try the next one, right? However, the data center networks are immersed. It's very large. There are tens of thousands of switches. Let's assume each switch has 1,000 rules, and then that's 10 million rules. And there are thousands of destinations. Worse, as your network grows, you suddenly have n times more switches and rules. And at the same time, you have n times more destinations. That means the overall complexity of your verification grows as O(n) squared. So how do we solve this kind of problem? One way to solve it is parallelism. We can use multiple machines. But the key problem of applying parallelism here is you need to partition your big problem into several small problems. And these small problems should be independent of each other so that you can run it on the separate machines. How do we partition this static verification problem to apply the parallelism? So in order to do that, let me go back to the forwarding graph abstraction. There are many very good properties of the forwarding graph. One is that each destination has a forwarding graph, and they are mostly different. And secondly, all data plane abnormalities are simply graph problems. For example, a loop is just a strongly connected component in a directly graph, and black holes are just nodes with positive in degree but zero out degree, etc. The third property is that the forwarding graph is not too big. The size of the forwarding graph equals to the size of physical network size. And this is because that each physical node is a vertex in our forwarding graph. And finally, for each graph, only a subset of rules are needed to construct this forwarding graph. In other words, not all the rules are relevant. So with the abstraction of the forwarding graph, we can develop this divide and conquer algorithm to partition the static verification problem. And I do this in two phases. First of all, you have this large forwarding graph that contains all the rules in it. In the first map phase, I slice this forwarding graph into several small subgraphs. Each forwarding graph is corresponding to a specific destinations. And I call this a map phase. And then in second phase, the reduce phase, each process can take a forwarding graph, do the graph computation, and generate a report. and this is the reduce phase. I call these two phases map and reduce because this can be implemented on the map reduce. So let's put everything we have discussed so far together. We have the stable snapshots. We have a route dumper that dumps all the routes from the data plane and store them in the distributed file systems. And these rules are sharded into several small chunks. And each mapper will take a rule chunk and then take a full copy of a destination and compare the rules against the destination and find out all the destination rule matches. A rule matches the destination when their prefix overlaps. And then it will output this intermediate result as key value pairs to the map-reduce systems. And map-reduce system will shuffle these intermediate results by their keys, which are the destinations. And then deliver all the rules relevant to a specific destination to one reducer. The reducer can now assemble the forwarding graph and do the graph computation and generate a report. So these are some evaluation results. We run the loop detection using Libra on 3 major data sets. One is DCN, which is Google's emulated data center network that has tens of thousands of switches and millions of rules. And then we have DCNG, which are 100 DCNs connected together in a star topology. And then we have INET, which is basically emulated ISP network that has 300 internet routers with full BGP tables. The point here is that with tens of thousands of switches, millions to hundreds of millions of rules, with the power of MapReduce and parallelism, we can finish the loop detection in the order of just minutes. Of course, we can do even faster than just minutes by applying the incremental updates. In this case, assume that all the rule updates is coming in, and we have a standing mapper sitting there and matching the incoming request with this subnet, and dispatch the matching destination rule pairs to a specific reducer. The reducer can then update this forwarding graph and collecting the result. And all of this can be done in an incremental fashion. And we found we have an implementation of this incremental version of Libra. We found that the mapping is super fast, and the mapper usually takes in the order of microsecond to find out the matching pairs, and the reducer takes in the order of millisecond in order to do this incremental graph computation. So that's pretty good. Depends on the graph size, of course. So time to sum up. Here I talk about Libra, which is a large-scale data plane verification tool that can run at the data center scale. Libra solves 2 main problems. One is the stable snapshot problems. It does that by only consider stable state of the data plane by discarding those shady area. And the second, and then it can avoid this false positive in the bad snapshots. The second is that Libra is a divide and conquer algorithm that can be implemented in MapReduce. It handles massive scale of data center networks by applying the parallelism. And that's all I have. And our data set is being open source on this website. And I'm happy to take questions. Thank you.
Very nice talk. Thank you. I'm Won from Cisco. Yeah. I think the previous talk and this talk is a very kind of 2 different sides of how to troubleshoot a network. One based on the complete dynamic data generated from the active network, and yours is actually based on static analysis, right? How do you think that how much portion of the problem is you can resolve with the static, or still do you claim that you still need you're not saying that actually you don't need anything we need to collect from dynamic network, right? So what's your perspective about this problem?
So there are basically 2 main problems in this troubleshooting area. One is called functional problems, which you can find out these problems by just looking at the forwarding tables. If you can do that, you may not want to send in the real packets or collecting postcards, things like that. You can use the static checker and does this passively. Another problem is another important class of problems like the performance problem. it can only be tackled in this dynamic checking field. And another problem is that sometimes this network their state is corresponding to the incoming packets. If that's the case, if the state of the network can be changed by the incoming packets, then you have to use these dynamic checking tools. So I think these two kind of tools, static checker and dynamic checker, they are tackling different problems.
You mentioned needing to account for inaccuracies in NTP, and I'm curious: are there switches? Obviously, you could do this in software, but are there like hardware switches that implement Lamport clocks? Because that's precisely the problem that solves.
Yeah, if all the switch has a global clock, so all these shady areas stuffs can go away. But in most of the network, the NTP is still very popular, and actually you can account for these different kinds of global clock synchronization by adjusting this epsilon value, right? Because the true global clock never exists. You can approximately go to a very accurate global clock, but it's very, very difficult to achieve that.
Okay.
So my question is about whether you can gather the events that you want from the sort of black box switches that we have today, or or you have to use the SDN style, like open switches to do that?
Yeah, as you may know, that Google is all about SDN. So this work is done on SDN by subscribing to these rule updates. It's easier to do that. However, the traditional networks is quite hard. So all these stable snapshot, it's very hard to implement. The best you can do is to try to do this snapshotting at roughly the same time, maybe with multiple route dumper to coordinate with them and dump all the forwarding tables at the same time to avoid this clock synchronization problem. But agree that in SDN world it's much easier.
But you can, so you have ways to just dump tables. That's the only control you got.
That's the only thing that you can do, because the control plane, these new updates, is highly tied to your hardware. And if they don't provide the API, then you cannot subscribe to these new updates. There's nothing you can do.
Okay.
Nothing much you can do.
Okay. Let's thank our speaker.
Can you use this to do testing on your controller software to feed it inputs? So before you roll out new controller software, you could use it to test to make sure it gets everywhere?
Yes. Actually, in that incremental update version, it can serve as an independent checker. And these rule updates, because they are sent in an SDN context, they are sending out from the controller. And you can route these events into the checker, check first before you install the rules.